Hey everyone, welcome. Today we're looking at a Leetcode problem called maximum value of an ordered triplet II. It sounds a bit mathematical, but don't worry, we'll break it down step by step and make it super clear. Let's figure this out together. Okay, so here's the task. We're given a list of numbers. Our goal is to find 3 spots in the list. Let's call their positions and such, that comes before strict order, right? Then, we calculate a score, take the number at spot, subtract the number at spot, and multiply that whole result by the number at spot. We want to find the highest possible score we can get from any valid triplet. There's one little catch. If all possible scores are negative, we just return 0. The list can be pretty long, maybe up to 100,000 numbers. So we need an efficient way. Let's walk through an example. Say our list is 12, 6, 1, 2, 7. We need to pick I, J, and K in order. What if we pick index 0, 4, that's the number 12, index 2, 4, that's the number 1, and index 4, 4, that's the number 7. Are they in order? Yep, 0 is less than 2, and 2 is less than 4. Good. Now, the score. We do number at minus number at times, number at, so that's 12 minus 1, which is 11, times 7, and 11 times 7 gives us 77. This is a possible score. The problem asks for the maximum score. In this case, it turns out 77 is the best we can do. Okay, what's the most straightforward way, the first thing we might think of? Well, we could just try every single combination of 3 indices, I, J, and K. We'd use 3 loops. The outer loop picks, the middle loop picks, making sure it's after, and the inner loop picks, making sure it's after. For each valid combo, we calculate the score. You know, number I minus number J times number K, and we keep track of the biggest score we see. But, with up to 100,000 numbers, 3 nested loops, that's roughly n times n times n operations. N cubed, that's going to be way too slow for the time limits. We definitely need a smarter approach. Let's rethink this. Instead of checking every single combination randomly, what if we focus on the middle index? Imagine we've picked a specific now. To make the score nums as big as possible for this particular J, what do we need? Well, assuming the result nums is positive, we want the number at, which comes after, to be as large as possible. And for the nums part, we want the number at, which comes before, to be as large as possible too. So for any given middle position, we're interested in the biggest number before it, and the biggest number after it. What if we could figure those out ahead of time? We could maybe create 2 helper lists. One list could store for each position the biggest number seen up to, but not including, that position. And another list could store the biggest number seen from that position onwards, but not including it. If we had those lists, we could just loop through our main list once, considering each element as the potential. For each, we'd grab the pre-calculated max before value, subtract nums, and multiply by the pre-calculated max after value. This sounds much faster. Okay, here's the Python code for that pre-computation idea using prefix and suffix maximums. Don't worry if it looks like a lot at first glance. We'll walk through the key parts slowly. First, this part creates our max before list. We walk through the numbers from left to right. We keep track of the biggest number we've seen so far. For each position I, we store the biggest number seen before we got to I. Then, we update our biggest so far tracker, possibly using the number at position I. Getting ready for the next step. It's like keeping a running high score. This next chunk does almost the same thing, but in reverse. It walks through the list from right to left. It keeps track of the biggest numbers seen so far, coming from the right. For each position I, it stores the biggest number found after that position. Then, it updates the biggest so far from the right tracker. This gives us our max after list. Finally, this loop puts it all together. It goes through each possible middle position. It can't be the very first or very last element, right? For each, it grabs the pre-calculated biggest before value from our first helper list, and the biggest after value from our second helper list. It then calculates the score, biggest before minus number at times, biggest after it. It compares this score to the best score found so far, and updates it if necessary. A small check ensures we only bother calculating if the biggest before is actually bigger than the number at, because otherwise the difference part would be negative or 0, which can't lead to the maximum positive value. At the very end, we make sure to return 0 if the best score we found was still negative. So how efficient is this first approach? Well, we scan the list forwards once to build the max before list. That's order n time, where n is the number of elements. Then we scan backwards once for the max after list. Also, order n. Finally, we loop through the middle elements once to calculate the scores. Again, order n. Adding those up, the total time is still proportional to n, so it's big O of n, or order n time, much better than n cubed. What about memory? We created those two extra lists, max before and max after, each needing space proportional to n. So the space complexity is order n. That order n space is pretty good, but sometimes interviewers push, can we do it using almost no extra memory? Like order 1 foot or constant space? Let's think about the calculation again. Number I, number j, number k. What if we loop through the list, thinking about each number as the potential last number? When we are considering nums, what do we need from the numbers before it? We need to have found the best possible difference part, the nums part, where both I and j came before k. To make that difference big, we want the number to be as large as possible. And the number, well, it's the number just before in the triplet. Okay, maybe we can track two things as we go. The biggest number seen overall way before the current spot, and the biggest difference, number I, number j, we could form using numbers seen so far. Alright, here's the code for the constant space approach. It looks simpler, right? Just one main loop. The magic happens in how we update a couple of variables inside that loop. Let's break down those updates. We start by initializing a few things. Ans is our running maximum score, starting at 0. Gax underscore. I will keep track of the biggest number we've seen, that could possibly be our nums. We initialize it with the very first number. Max underscore I underscore minus underscore j. We'll track the best difference part, nums minus nums, that we've been able to make so far. We initialize it to 0. Now the core loop, we start from the third element, index 2, because we need at least I, j, and k. Inside the loop, k underscore idx represents our current. First, we think about the number just before it, nums underscore idx1, as a potential. We see if we can make a better nums difference using the max underscore I we knew before this step, and this potential nums. We update max underscore I underscore minus underscore j if we found a better difference. Second, we update max underscore I. The number nums underscore idx1 that we just considered as could also be the best for some future triplet. So we update max underscore I if nums underscore idx1 is bigger than the current max. Finally, we calculate a potential score for the current k, nums underscore idx, using the best max underscore I underscore minus underscore j difference we've found up to this point, and update our overall answer ans if this score is better. And the efficiency of this second method? We loop through the list essentially once. So the time complexity is still fantastic. Order n. But the space? We only used a handful of variables to keep track of the maximums and the result, regardless of how big the input list gets. That means we've achieved order 1 foot or constant space complexity. That's about as good as it gets. So let's quickly recap. We needed the maximum score from an ordered triplet using that specific formula. The naive way of checking everything was too slow. The first smart idea was to pre-calculate the maximum number before any given spot and the maximum number after it, allowing an order n time solution but using order n extra space. The even cleverer approach involved just one pass, keeping track of the best seen so far and the best I minus j difference seen so far, which gave us order n time with only constant, order 1 foot, extra space. And don't forget that 0 rule if no positive scores are possible. Hope that explanation helped you understand the problem and the different ways to solve it. If it was useful, feel free to hit the like button, subscribe for more coding breakdowns, or leave a question or comment below. And hey, if you're feeling extra awesome, the Boba Fund link is always appreciated. Keep practicing, keep coding, and I'll see you in the next video.